We got a guest here today, Mario. How's it going?
Doing okay.
Welcome,
I
man.
mean, it's great to be here. I'm glad to join you guys after interacting so much in on the Facebook page. We never had a chance to to talk to each other
Sure.
and like
Yeah,
to
yeah, yeah.
Welcome, man.
have some
It's
Thanks
fun.
for coming.
awesome to be able to finally talk to you in person, or kind of in person, on
Yeah,
camera.
yeah. This is as close as we can get for now.
Right. Close enough.
So you study black holes quite extensively, and that you do that as a career. And so we're gonna dive into that, but we're not gonna go into it just yet.
Way to tease him.
But I'm incredibly interested on what he has to say here. I'm dying to know all of this. I don't even know where to begin with it all, but of course, you'll take it away when we.
Yeah.
Hey, I don't even know, and I'm the one studying it.
It sounds insane, which it is insane. So
It
Yeah.
is. I'm losing my hair just little by little.
You'll be like me soon enough, man. Don't worry.
Oh man, I'm almost there. Trust me. I'll be there in no time.
But any new guests that we have, I like to ask some sort of gamer questions about your history. If you were to just pick your favorite console just all time, what is it?
Whoa.
Good question.
Favorite
PC.
Just favorite video game console.
Okay, if I have to pick one, I'm gonna go with the PS2.
Oh,
I think
good
Okay,
choice.
okay.
it has such an amazing library. I
really
mean,
does.
it's not the one that I grew up with. I mean, I'm an old school gamer.
Right.
I've been gaming since the Atari days.
Okay.
I'm an '87 kid.
Yeah.
Okay,
Yeah.
I'm 88.
89.
hmm
There we go.
Oh, okay.
Oh wow! So 87, 88.
We're all pretty
89.
close age.
Yeah.
So you had an Atari first when you were a kid, because my first console was an NES. I didn't have an Atari.
Yeah, I had an Atari just because I got it from a friend. I was born and raised in Cuba, so like in Cuba, it's
Okay.
just like whatever you got your hands
Right.
on, that's you have to be happy with that. We
Yeah,
didn't
yeah,
have a
yeah.
lot of options. It's not like I could go to a store and buy whatever console I fancied. It's just like whatever I could get my hands on. And the first thing I got was an Atari, and then an NES, and then from there,
Yeah,
Awesome.
yeah.
I always go between PS1 and PS2 on which one I would pick. So PS2 is an awesome pick.
Well, yeah, you can't go wrong with either. Yeah.
Yeah.
I would go way different than both of you guys. I would go to Super
wow.
NES. That's my go-to.
Oh
I
man, actually,
I love that system.
I mean, that's
so
really
much, man.
good. That's really good.
Don't get me wrong.
actually,
PS2.
that would be either my second or tied with for number one
Yeah.
with the PS2. I love the SNES.
Dude, there's so many.
So I
so many
still
great
have
games.
a Super Nintendo. Do you guys have a Super Nintendo? I got
No,
one.
I don't collect anything.
I don't
Yeah.
collect them anymore, but I think I have one somewhere, and it's yellow. It's like yellow, like Mario's chair, because of
Yeah.
all the
Mine
years
too.
of it fading. And because
Is it cyberpunk?
yeah,
yellow,
it's
though?
not cyberpunk yellow. It's not there yet. But yes, I think SNES is, man, some bangers. on
SNES
that
was
system.
that was my jam. Yeah.
Oh yeah.
All right. Well, one more question here. Just off the top of your head, if you were to just list your top 5 games, like it could be a series, it could just be the game itself, but it just like, what's your top 5 games? Now, which obviously I understand how hard these questions are. You're not going to actually be able to
Oh,
give
for
a
me,
top
it's not
5,
hard at all. Like,
but just go off the top of your head here. Top 5.
right.
What-
So for
what comes
number
to mind?
one, and this is a tie. That just don't make me choose because I cannot possibly
Okay.
choose. For
Okay.
number one is Metal
I
Gear.
knew,
the
I
whole
knew it. I
series,
was gonna guess. I
Yes.
was gonna guess. Damn.
I love you.
and Mass Effect. Yeah, Metal Gear and Mass Effect. Those are my favorite series.
Nice. Good choice.
Then after that, after Metal Gear and Mass Effect, well,
So
then it
Metal
gets
Gear is
tough.
in mine too, by the way. I'm a
Yeah,
huge
oh
Metal
man,
Gear
I
fan.
just love that series so much. After that, man, it gets tough because I mean, there's the Soul series, but it's not really a series because you have like Dark Souls.
But
and
you
then
are
Bloodborne.
big into this. That's cool. I didn't know that. Okay.
Yeah. Zelda and Metroid, yes.
Nice.
Metroid
Metroid.
even above Zelda, actually. Metroid is my
Oh, wow.
Love
favorite
me some Metroid.
Nintendo franchise. Yeah, I
So
love.
you play
Metroid.
Dread, right?
Yeah, well, that's a question that I started it. I'm actually
Okay.
playing it on PC with an emulator, and it's
I'm sure.
Okay.
It's all right.
Well, that's how I played it too. By
It's
the way.
amazing.
I
The
played it
thing-
in 4K 60. It was
Yeah. I'm playing it also at very high settings, and it's amazing.
Yeah.
And right now, I'm in the middle of doing a lot of stuff at the university. I'm like, I barely have any time for
I got
gaming.
you.
So the games that I'm playing now are games that are more linear, or maybe something open like Far Cry 6, for example, because it's like it's open.
Easier
but
to jump in and jump out.
it's very easy
Yeah.
to jump back in because you don't really care about
Right, it doesn't
where
matter.
you were before. Yeah, but with Metro, you're gonna be so lost. You're gonna be like, you're gonna have to revisit every single room to see where you have to go
Yep.
Yep.
next.
Yep.
So that's why I stopped. I'm at the very beginning, and from what I played, I love the game. It's amazing.
Yeah.
All right, we're going to get into the main topic of the show. He's going to explain his deep research into black holes, and I don't know anything about this, which is very exciting because I want to, I want to hear what it is you're even doing exactly, and where your goals are of like as a whole with your company and everything. Where what are y'all exactly trying to figure out and do and all of that stuff? So
I'm just gonna start by saying I'm already regretting the interview because I don't know what I'm doing and I don't know what I want to do next. So this was a terrible idea.
well, make something up,
No, just kidding. I mean, it's like at times you do feel like you don't know
I'm
what you're
sure.
doing, but it's
Yeah,
that's
I
how
got
it
you.
is, man. It's a struggle. I'm currently doing my PhD in the program is called mathematical modeling. So basically, we have people that do models of things that have nothing to do with astrophysics. People do modeling of biomathematics, like cancer research and stuff like that. So
Okay.
there's people that are doing all kinds of stuff. But I'm mostly interested in astrophysics applications. In my research group, we focus specifically in black holes. There's a lot of people in the astrophysics department that are doing neutron stars. Other people are doing black holes. Other people are doing, I don't know, they're looking at the pulsar timings and stuff like that. What I do in my research is black holes. So specifically, the field is called numerical relativity. So it's
Wow.
like a numerical implementation of general relativity, the
Okay.
Einstein's theory of gravity.
Right. Right.
So basically, the bottom line is that the Einstein equations, right? It's all about solving the Einstein equations.
Right.
The Einstein equations are very complicated. They're so complicated, in fact, that in order to solve it, unless you're looking at a very particular case where you can make some symmetry assumptions. You assume that, oh, I'm looking at this object in the sky, and the object has spherical symmetry and it has no rotation and this and that. Then you can come up with some, what I call analytical solutions, meaning those are solutions that you can solve by hand with pen and paper.
I see.
Very hard to solve them, but it's entirely possible to solve.
Quick interjection. Do we ever find out if Einstein was actually a genius or was he just really intelligent? Do we even know to that level? Was he actually?
I mean,
Because
both. I mean, he
people
was a
like, hey,
genius.
a genius, and they can read a whole book and recite it back or something like that.
Right.
Was he that far?
That I honestly don't know because I admire his work. Obviously, I'm dedicating my career to study his equations, basically.
Okay.
But
I was just curious.
Yeah, but I don't. Like some like people outside of the scientific community, they make a big deal about these extraordinary people that have the ability to do things that are
Yeah, it's almost like a special power or something.
Yeah, exactly. But in reality, it's doing science is much more than that. I'm not saying that this is
Yeah, I'm curious if he had that superpower.
This is
or
better
not,
than this or that is better than that. I wish I had some superpowers. Trust me, I wish. But what I'm trying to say is that the fact that someone can I don't know multiply in their heads like 4 billion times, 3 trillion times, whatever, so that they can do the math in their head. That doesn't really mean anything. I mean, it's great. I mean, good for them. But it doesn't really mean anything in the sense that you don't know if this person has this skill, which is very, unnatural. Like it's great that this person has this skill, but that doesn't really translate to like
to
doing research or like solving some real world problem. You know what I mean?
Okay. Yeah.
So as to whether Einstein was some kind of genius and he had like something different in his brain or not, I leave that up to speculation. All I know is that his physical intuition, his intuition about physics, was second to none.
Sure.
Like he was always thinking outside the box, and that's what made him a great scientist.
Yeah, it's
because he was
incredibly
always,
impressive. We're
yeah,
still trying to figure out what he solved basically in
yeah.
his own mind. Now, you can only spell it out so well for other people to understand. So I get all of that. And now people have to spend all of their life trying to understand what he was thinking, kind of
Yeah, yeah,
level.
yeah. The way that he came up with this theory of relativity,
Right.
before general relativity, he came up with a theory called special relativity. The difference between the two is that in special relativity, you're not taking gravity into account. You're looking at a space,
Okay,
Okay. It's like
a
space. Okay.
flat space time, but the whole thing about the special relativity was this idea that time and space were one and the same. They were two sides of the same coin, basically,
Right.
if you will. So, and then after that, that was in 1905 when he came up with the
okay,
theory of special relativity.
Right.
And then it took him 10 years. It was in 1915 when he was able to finally reconcile the, gravitation, like gravitational physics, with the theory of special relativity.
okay,
So
cool.
it took him 10 years to get there. And as a matter of fact, I mean, he needed this is, people give Einstein all the credit. He deserves a lot of the credit because he's the
Right.
one with the intuition to come up with this idea. But the reality is that there's so many people behind this because
Sure.
he went to one of the greatest mathematicians
Okay,
of all time, David Hilbert, a German mathematician. He's the one who first solved the Einstein equations in a very mathematically
I
rigorous
see.
way.
okay,
You know what I
cool. I
mean?
didn't know that.
In general relativity, all the theory of gravity is based on a branch of math called differential geometry. Differential geometry dates back like way before Einstein. So
Sure.
it's not that he came up with all the mathematical background, like all
Right.
the mathematical ideas to come up with general relativity.
Okay,
All of that was already done.
Right.
He just had the intuition
Kind of
to
like put it together.
to put it all together and connect all the dots. Basically, there's differential geometry, and then Bernard Riemann, a very famous mathematician from the 1800s, he came up with an extension of differential geometry that included like curvature and stuff like that into the differential geometry, and that's what is called Riemannian geometry.
which you have to use that when it comes to black holes, obviously.
Yeah,
Yeah,
absolutely, because you're looking at the curvature of space-time.
exactly. Yeah.
Basically, the Einstein equations are a relation between how much a region of space-time bends, how much curvature there is, and in terms of how much matter slash energy there is in this space. It's a relation between matter slash energy and the curvature of space-time.
Can I ask? So, in my limited understanding of black holes, right? Because as you guys know, I'm a fifth grade teacher. Okay, a math teacher. So I try to delve into, like, when I do science, I try to delve into the topics that I find interesting. So we
Mhm,
did black holes. We've been doing it every year,
mhm.
and to the extent that I can go to is I can do some research online, try to understand what a black hole is, make a fun way to teach them, and then we talk about it. So I was hoping maybe you could explain to me what exactly is a black hole in your own words,
Yeah,
because
yeah.
my
Right.
understanding of it, this is my very, very rudimentary understanding of it. I'm probably gonna get this wrong, but a star at some point will die or explode, and then something happens with basically that whole area becomes so the pull is so strong that anything that would be go into there would just, like, then that space-time term comes up, but I don't really understand what that is. And then eventually a black hole is formed. Now, something along those lines. Now, you tell me.
Well,
You tell me
I want
that.
to ask one thing too.
Okay, okay.
To what I thought it was the proof of nothingness. If they, understand what I'm saying, like,
Yeah, yeah,
there is there's basically an object full of nothing, and that's what a black hole is.
but you're not that far off, to be honest.
Okay.
Before explaining anything, let me say, Rudy, you're doing God's work. You're doing a great job because
I
this is
appreciate it.
this is so important. Forget about like knowing all the nitty gritty details, like the underlying math or whatnot. Just
Right,
the fact that just
He's
getting kids,
sparking something
getting
in
kids,
kids.
right.
Yeah.
They're
exactly, yeah,
getting
just
interested in that.
getting kids excited about this
Yeah.
topic.
Sure.
This is great, man. This is great because this is how it all starts.
Yeah,
If a
you're right.
kid
You're right.
if a kid is not exposed to all of this early on, chances are that by the time he gets
Mhm.
to he or she gets to high school or
Right.
college, they won't really care. They will be
Yeah.
looking at
How would they
something else.
even know to care
Yeah.
if they never saw it? Yeah,
Well,
Exactly.
I appreciate you saying that. Yeah, I that's my goal. I want to get the kids excited about cool topics like that. There's even some girls who I see them excited about. I'm like, this is cool because I know it's not, it's not as prominent to see girls grow up and
Yeah.
go do things like that. So,
Yeah, exactly. And
yeah.
I myself, I mean, like I told you guys earlier, like I grew up in Cuba, and like people don't. When was the last time you heard about this famous astrophysicist from
Cuban
Cuba?
astrophysicist.
Like
Yeah.
no one cares about any of this stuff. Every time I say that I'm working on black holes, the people just make fun of me because you know what I'm gonna
which
say.
makes it even
I
cooler
won't
though.
even say.
That's awesome. The fact that
Yeah.
you can go to drive even though people around you aren't really pushing you to do that, but you have that drive anyway. I mean,
But
that
that's
speaks a
that.
lot of,
This is exactly why I'm saying that I really appreciate the like
yeah, yeah.
Rudy's job, because if I had someone telling me about all this cool stuff early on, I would have gotten into black holes a lot earlier.
Yeah, that makes
Thing
sense.
is, I had to start college, and like I jumped around. I was first of all I was a history major, and then I changed to geology because I really liked rocks. And then at some point I had to start taking math courses because I was looking at the graduate programs in planetary science because I was doing geology. I
Okay.
was and I was getting interested in, okay, maybe I can get into grad school and pursue a degree in planetary science. And then I saw all the requirements varied from school to school, but the bottom line is that all the programs, they require math. Like you needed to have a certain level of math, like up to vector calculus and stuff like that. And I said, whoa, you know what? I'm not a huge fan of taking math courses, but I have to if I want to get into one of these programs. And then I started taking math, and I started to like it, and I like it more. And next thing you know, that's where I went completely into math.
So
It's very
both
cool.
me and Rudy are really big into math. I
I love math, man.
of all subjects, it's weird. It's grammar and it's math, and they do kind of similar
Yeah,
things because
they work
you're
together.
solving equations with either
Yeah.
one.
Yeah.
So,
No,
yeah.
so let me tell you, because I know that we're going on a tangent, but this is important. This is
Yeah, yeah.
important because I want people to understand when someone says, "Oh, I'm not a math person," they don't know what they're saying when they
Oh my
say
God,
that.
totally agree with you so
And
much.
I'm telling you,
Yes, yes.
I'm telling you that for a fact because I wasn't a math person. I
Right.
hated math when I was in high school. I did not want to deal with math at all. I needed a motivation to get into math. What was the
You could be
motivation?
like
I
into
just started like,
psychiatry, and
yeah,
because you're trying to solve a person's issues, that's technically all math is really doing.
yeah.
It's just trying to
Yeah.
solve a situation,
Yeah,
right?
and any kid watching this is say, "Oh, I hate those word problems." Like if Peter has 20 cents in
Right,
his
right.
pocket, hey, trust me, I hate those too. I,
Yeah, yeah.
I hate like all the math that they give in high school and like before that is so boring. Like
Yeah.
even in college, like the more elementary courses, they are really boring.
Yeah,
Math
like the
starts to
101.
get
Yeah.
interesting after calculus, but you have to, at that point you already have a barrier because at that point kids are saying, no, I'm not into math, I'm not a
Right,
math person,
right. I'm not a
why
math
would I bother getting into calculus? I'm gonna fail. But
I
man,
love that you said after calculus because it was an episode or two ago, and I was telling Rudy the one subject I hated was calculus.
calculus. Yeah, the kids know not to say that in front of me because they know I'll stop the whole lesson and be like, "What'd you just say? You're not a math person?" And they're like, "Okay, we get it. Okay."
on this note, man, and this is the last thing I'm gonna say before I go back
Yeah,
to
yeah,
black
yeah.
holes.
All
But
right.
on this note, let me tell you, I have a friend of mine. We went to college together. We both graduated in math. She hated calculus, and she still finished a math degree, but she hated calculus and she did horrible in all the calculus courses. But guess what? She was brilliant in abstract algebra, in another topic in
Yeah, yeah,
subject in
yeah.
math, and she ended up doing a PhD in abstract algebra. She already graduated. So the bottom line is, again, when you say I'm not a math person, I don't like math, you don't know what you're saying because there's so many different
Mhm.
subfields within
Right.
math, and
Right.
you're not gonna like all of them. There's a lot of things in math that I don't like. Don't make me get into like combinatorics, graph theory. I don't like any of those topics, and it's still math. I don't
Right.
like probability. I hate probability,
Yeah.
and it's still math. So yeah, when you say that, you don't know what you're saying. That's the bottom.
Let's speak
Agreed.
to the nerds
Agreed.
here. It's like video games, right? I mean, how many genres are there, right?
Exactly.
Like,
Oh, yeah.
it's like saying, "Oh, I don't like video games because you don't like racing games." Like, well,
Right.
there's plenty of other genres you could enjoy. Like,
Yeah, my wife hates gaming, but she loves getting on Beat Saber and just
Right. There you go. You're a gamer now.
Yeah.
Yeah.
There's always something for everyone.
yeah.
Something like whatever that is, there's gonna be something.
Agreed.
So yeah. Anyway, let me see if I can.
What is the black hole?
Yeah. What is it? What is
What
a black
is
hole?
a black hole? Yes.
There's a very simple answer. Actually, I don't know.
Okay.
No one knows. That's it. That's the bottom line. That's all you need to know.
Interesting.
Close out this episode. We're done. So the thing is, we don't know what it is because it's a singularity. It's a piece of information that is missing from the fabric of space-time.
Okay.
It's a point where all the math breaks down, everything breaks down. So when we say that we are studying black holes, we're doing research on black holes, what we really mean is that we're doing research on the vicinity of the black hole,
I see.
Everything
on
around
the
the black
surface of the
Okay.
black hole, like on the apparent, on the what is called the apparent horizon, right? The horizon of the black hole, which is what you see as something black, right? So like anything that goes into the horizon, it's completely gone.
It's like imaginary numbers. You have to solve everything around it.
Yeah. I mean, imaginary number. This is another topic that, when it first came out, there was a lot of controversy. A lot of people just didn't want to accept something as outlandish as something being imaginary. I mean, math is all about being exact, right? It's an exact science. So the thought of maybe there's something imaginary that didn't sit right with a lot of people.
But we have proved it at this point that
there's a big theory called complex analysis where you can do a bunch of stuff there, and we use it in just about everything in a lot of branches of math, not only in complex analysis, but we also use it in numerical methods. We use it when we look at eigenvalues of some matrices and stuff like that. It's a really important concept. And
Matrix, I always like dealing with Matrix. It's really cool.
Because you love the Matrix trilogy. You love the movies, of course. The name is cool, right?
No, it is really interesting. You're able to solve so many things because of a matrix. It's really awesome.
It's incredible how many problems in math all boil down to solving a linear algebra problem. So you start with something like a differential equation of this type or of that type or whatever. And it all boils down to solving a linear algebra problem where you have a matrix and a vector and another vector, and then you're trying to solve for one of the vectors. That's like 90% of the problems that I have to deal with.
Okay, can I ask real quick? I don't know if you mentioned or not, but the whole concept of space-time then. Can you explain that to me? Because that also, I don't understand it.
Right. So basically, if you look at, forget about all the general relativity, forget about all the stuff.
Right.
Think about, three-dimensional space, right?
Sure.
So X, Y, and Z plane, right?
Yep.
X, Y, and Z. Well, not a plane. X, Y, and Z space. Okay.
Okay.
Imagine that you just. Okay. Let me just say this because the more complicated part is going beyond 3 dimensions because our brain just can't wrap our heads around that. So forget about 3 dimensions. Let's talk about, instead of having an X and Y coordinates, just like two-dimensional plane with an X and Y coordinate, let's talk about having an X coordinate and a T coordinate, where T is the coordinate of time, right? So we have one coordinate of space and one coordinate of time, right? Now, we have this situation where we have X and T, and we have the usual situation where the two-dimensional plane that we're dealing with, it's X and Y, right? Okay. How do you find the distance between 2 points in a Cartesian plane in the XY plane? You do like X minus X naught, square plus Y minus Y naught square, and then you take the square root of that. That's just one example of the what is called the Euclidean distance function, right? The metric, the Euclidean metric. The only difference when you jump to something like the TX plane, where now you have a time coordinate, is that now you have a different signature, is what it's called the signature. You have a different signature on the metric. So now you have one dimension, it's going to be positive, and the other dimension is going to be negative. So instead of having X minus whatever square plus Y minus whatever square, and then taking the square root of that, now you have minus T minus something square plus x minus something square, and then you take the square root of that. So basically,
Okay.
you're introducing a new signature to the metric,
Okay.
to the distance metric. And it always turns out that in the case of relativity, we use what is called the Lorentzian metric. The Lorentzian metric is all the space, the dimensions are going to have positive signature, and the time dimension is going to have negative signature. And it
Okay.
sounds like something very small, but it sprawls out into this huge field that it gives you very different results.
That's
Because
interesting.
just to give you a brief example,
Sure.
what think about flat space. Okay, in flat
Okay.
space,
Okay. Yeah.
what is the you pick 2 points.
Right.
What is the fastest way to get from one point to the other?
Go straight across,
Yeah,
right?
just draw a straight line, right? You just draw a straight line, and that's the shortest path between the 2 points.
Right.
It turns out that when you add this new signature, the negative signature that comes with the Lorentzian metric, this this line that is going from one
Yeah.
point to the other is the longest distance, the longest possible distance between 2 points. It's all
Wow.
the opposite,
Interesting.
Okay.
right?
Okay.
And the extension of this to curved space or curved space-time, the extension of the concept of a line, is something that is called a geodesic. So in flat space or flat space-time, we talk about the lines. As you talk about you draw a line from one point to the other. In the case of manifold, what is called a
Yeah.
manifold, you have what is called the geodesic. It's like the the analog of the straight line in curved
It
space.
would be the most proficient way
Right.
of
So if
that.
you have a sphere and you have 2 points on a sphere, there's no way that you can draw a
Right,
line between
right.
2 points
Yeah.
unless you're going through the sphere, right?
Right.
You
Yeah.
have to puncture the sphere if you want to draw a line between them.
So we have to
But
curve.
you can do like this curve that goes from one point to the other, right?
Okay.
Right.
And if that curve is in a certain way, it can be called a geodesic, and that will give you the shortest distance between the
Okay.
2 points.
I see.
So this concept of the geodesic, when you go to space-time with the negative signature, is going to be the longest.
Okay.
I know it's confusing, and I get it. I mean, this is
It's confusing, but it also makes some
I'm
sense too.
explaining all these things without even a whiteboard, so it's really hard. But let me give you just to give you some food for thought and give you some homework. When you have
Okay.
some time, just Google the twin paradox.
The
Twin paradox.
Okay.
The twin paradox.
I love
Just Google
paradoxes.
it. Just
Okay.
Google it and read it. You can find, like, even on Wikipedia, it's explained in a way that you don't really need to know relativity to understand it.
Okay.
But it's actually it's going to explain what relativity is all about without having any prior knowledge of relativity.
Okay.
And it's
So I
going
mean,
to
a paradox in general is something almost beyond comprehension, much less a twin of paradoxes.
So no. When you read it, you're gonna see why it's called the twin paradox. It's not.
Okay,
It's about
okay.
two twins. One of them goes, he goes to another planet or whatever, and then he comes back to Earth after X many years. And
Oh,
when
okay.
he comes back, he's a lot younger than his twin
Right.
brother.
Right.
And
Okay.
you're gonna see why this is. At the end of the day, is because the one that stayed on Earth, he followed a geodesic path, and the other one didn't follow a geodesic path because he had to accelerate to go out of planet
Okay.
Earth and then come back. And again, because the geodesic is the equivalent of
Of the
the straight
straight line.
line.
I'm
And
guessing
in
the
this,
other guy got there faster. Is what
yeah, so
you're trying
this
to
other
get
guy
at?
got faster
Okay.
because this, in the case of Lorentzian space-time, this geodesic gives you the longest path between
Okay.
2 points. So yeah, so the one who stayed on Earth is older than the one that moved away.
That actually makes
That's
sense.
pretty
right?
cool. That's
Okay.
pretty cool.
So if I was here on
Yeah.
Earth and you went close to a black hole and then you came back, when you come back, everyone you know and love will be gone. Will be long gone.
Oh, Jesus.
That's the bottom line.
Whoa,
Okay.
that's kind of crazy to think about.
Yeah. So no one knows what a black hole is. But the first indirect proof of a black hole was due to something called gravitational lensing. So you have, like, you're looking at the sky, and obviously, if something out there is black, you're not gonna see it.
Yeah.
But the thing is, these black holes, they are so massive, and the gravitational pull that they exert on the neighboring objects is so
Okay.
strong that you could see like stars that were moving around a center of something.
Okay.
But then when you look at the center, there was nothing there. So that's an indication that's an indirect indication that there is a black hole there.
Yeah.
It's black because we don't see it, but we know it's a very massive object there because we see the objects rotating around it. And then the gravitational lensing stuff, it's just like lights that are coming from stars or galaxies. They are being bent as they pass through a black hole. So you see the bending of light, and
Okay.
due to the gravitational pull of a black hole.
So in film and all of that, they actually can portray it pretty, like, because they will literally bend light with the on film, and
Right.
it gives a good idea. I was always like, is that how it actually works, or do we just
Yeah.
just
Gravitational lensing is very real.
Okay.
That's a fact. That happens. But again, it can only be a black hole because light is. I mean, there's no way to bend light without a huge amount of gravity, and no object in the universe has more gravitational pull than a black hole.
Now I
Well, a
know
supermassive black hole, but yeah.
Right.
many answers to this, but I'm gonna ask you, what is the drive here when it comes to figuring out more about this black hole? Like, what are people, you think, trying to get out of it?
That's a very good question, because we mathematicians, we pride ourselves on being useless. The more useless we are, the better. but honestly, here's the thing. It's true that this is mostly academic. I mean, like, we're not gonna be able to travel to space anytime soon.
Mm-hmm.
But hey, man, if we have to advance our knowledge,
Every step matters.
every step matters along the way, because if we don't do this research, we are never going to leave this planet. We're never going to advance. And guess what? A lot of times you're studying things that are like very theoretical, like things that are very out there. And one day, or maybe soon, maybe not soon, maybe after you're dead, most likely after you're dead, after you're long dead, someone is going to come up with an application that is applicable to something like more hands-on, out of something that is very theoretical. Let me give you two examples. One is in abstract algebra. There's this topic about cryptology, I think is what it's called. So basically, it's all abstract algebra. If you read anything about abstract algebra, like, the name it implies everything. It's really abstract. There's nothing applied about abstract algebra. It's really, really out there. And it's like one of the most pure math subjects you can take in college.
Okay.
It turns out that if it wasn't for abstract algebra, there wouldn't be, like, cryptology. There wouldn't be cybersecurity. You wouldn't be able to use your debit card, your credit card. So there are people who always find some, hands-on application to something that is very abstract. Now, the job of a pure mathematician is not to worry about whether someone is going to use their work or not. This is up to someone else, to find a use for day-to-day, usage.
It's almost like a thankless job, kind of sounds.
Yeah. We just do our thing. We concentrate on our work, and then if someone else finds a way to to make our work applicable, that's great. But if not, then so be it. In the case of general relativity, for example, there's two big theories of gravity. The first one is Newtonian gravity. That's what everyone, when they start learning physics, they study Newtonian gravity. Newtonian gravity is a very decent approximation to the real deal, to gravity, as is general relativity. It's not an exact theory because we're still missing the link to quantum physics, but that's another story.
Okay.
But Newtonian gravity is actually is very good for our day-to-day use. We use it in many things, to do calculations here on Earth, even calculations at the level of our solar system. You can also use Newtonian gravity to some high degree of accuracy. Now, when you go outside of the solar system, when you're studying like the galaxies and and black holes and stuff like that, you do need general relativity because Newtonian gravity is too limited. It's not it won't give you not even close to correct answers when
Okay.
you get to that stage. But there's something right here on the planet that we use every day, right? That you do need general relativity for, and that is the one thing that you always find in general relativity textbooks when they talk about some hands-on real life application. This is the only one that we can come up with, so I'm sorry. GPS. You know, if you did the calculations needed for GPS, location, if you used Newtonian gravity to do those calculations, you will be way off. So if you see something on the map that shows that it's here, it would actually be all the way out there. It would be like miles away, you know? So to pinpoint with such accuracy from the GPS, we need general relativity.
Now,
Because
how
it's a
does
much
GPS work then? Like, I mean, we know the general ways, but you think you could explain it better for like, okay, yeah, the satellite image shooting it so we know when to turn and how soon and how late and all that. But what exactly is, like, is it a signal coming from a satellite to our device and that's all it is? What more is going on?
let me tell you, I know just about as much as you do.
Okay.
There's this one thing, like there's a divide in the physics community. There's the people who do the instruments and stuff like that. They build the GPS satellites. They build the particle colliders. They build stuff, you know. They're engineers and people who do calibrations of all these instruments so that we can put our theories to test, you know,
Okay.
basically. So I'm in the theory part. I don't know much about the, you know, what exactly goes on in
Okay.
in the engineering of all these things.
Yeah.
Interesting.
Yeah. So the other thing that people are using now to detect black holes, and this is not indirect. This is very much a direct observation, which is something new. So the news that you were talking about earlier,
Yeah.
this is from 2015. That was the first time that we actually detected gravitational waves on the planet, on Earth. And not in an indirect way. It wasn't through gravitational lensing or anything. We detected the waves. And this
How
is
did
using,
we detect the waves?
yeah. So this is using an instrument called an interferometer. So an interferometer is like something that is on the ground. It's like huge. It's like miles. It has like two legs. So like both legs go for miles and miles and miles.
Is
And they
this in the
basically,
United States?
there's two in the United States,
Okay.
LIGO, LIGO, LIGO. There's another one. There's a big one in Europe too that is called
Okay.
Virgo, like Virgin, but with
Yeah. Okay.
Virgo. And there's a couple more that are being built and whatever. And there's one that is really exciting that is gonna be launched in the 2030s, which is called LISA, which is gonna be a space interferometer. So we're gonna be launching this thing that here on Earth, it's miles and miles long. We're gonna find a way to put something like that in a
Like
smaller
10
scale.
miles, 50 miles, 100 miles? What are we talking
Yeah,
about?
but they're making it at a smaller scale. But
Okay.
you know, trying to avoid losing accuracy as much as possible.
Okay.
And they're gonna put this thing in the sky, so it's really exciting. And we need that. We need that because the atmosphere here on Earth, it blocks out a lot of the electromagnetic waves that are coming from space, right? So we can, for
So if we
instance,
can get it out of the ozone, we'd be a lot better off on reading.
exactly, because if you think about it, like look at on the electromagnetic spectrum. If you look at the highest energy end, you know, like ultraviolet, X-ray, and all this stuff.
Yeah.
This is, thankfully, this is not reaching us. This is not reaching the
It's
ground.
protecting us.
Right?
Yes.
We have an ozone layer and all that. You know, we have things in the atmosphere that is protecting us.
Right.
So, but the thing is, for the sake of doing science, it kind of sucks because we want to get those. Just like if you look at from a telescope, we look at the stars, we look at galaxies, but that's in the visible range, right? And then you have telescopes that are like on the infrared range, which is like the lower energy range. But if we want to have like an X-ray or gamma ray or something like that, a detector, it cannot possibly be here on the surface of the
We need
planet.
to get past that imaginary wall we have. Yeah.
Check that
That's
out.
why-
Found a picture of what Mario was talking
Not
about.
imaginary.
Just in case you want to take a look. It's really
Invisible.
interesting, actually. That looks freaking. It's just crazy to look at. That's how big it is. Mario, can you see in the chat?
I opened it. Yep, yeah, this is exactly where it
Wow.
is. This is explaining to you what the interferometer is.
Ah,
It shows you the two legs and how the wave is detected and
crazy, man.
everything. So the thing is, what we do, like what I actually do, is I work on the theoretical part because we need to build a catalog of gravitational waves, so
Ah,
that we can kind of filter and match the gravitational waves from our numerical simulations to the to the signals that these interferometers are receiving. You
Okay.
know,
gotcha.
because they're the when you get all this noise, when you get all this signal, there's always a lot of noise in the signal, and it's kind of, I mean, without any point of reference, it will be hard to tell what is a gravitational wave,
Right.
or maybe it's not a gravitational wave, maybe it's something else. So you need to build a catalog of waveforms, gravitational waveforms, in order to, to match and all that. So basically, in a computer simulation, you say, okay, let's start with these two black holes. This one has mass whatever, this one has mass whatever, they have this much spin, this much angular momentum, linear momentum, whatever, and then you do the simulation, and then you get a gravitational wave. So you send that to the catalog of LIGO and Virgo and all the stuff, and when they receive signals, those signals are automatically being processed and compared to all the signals that are already in the templates. They have like all this catalog of gravitational waveforms that were given by research groups like ours, who do the numerical simulations, and then they compare that to what they're getting from the interferometers, from the detectors. And then if you have a match, great, you found the black hole.
Okay. When I was like early
Yeah,
teenager, I
collision
remember
of black
this
holes.
story about them getting close to being able to like create one, but it got like way too dangerous and they pretty much like couldn't continue anymore. Do you know what I'm talking about? It was
What were
like
they creating? Creating
they
what?
were trying to create a black hole. Now,
Oh,
obviously,
whoa.
it's all just a matter of theory, and there's no way to just actually just straight up create one. But I remember seeing, and I was really into it, and I kept looking up a ton. And this was like dial up internet days. And I was trying to find article after article, and I was reading about it for like days on them getting really close to making it happen.
Interesting.
And they ended up getting shut down. And this was like in like the late 90s. And do you have any idea what I'm talking about or what
Yeah,
the.
yeah, yeah. I mean, it's entirely possible. It's entirely possible because at the end of the day, there's nothing special about black holes in the sense that this is not like, oh, this is some object that was created in the sky or whatever. You can create a black hole as long as you have a certain mass, like a certain object that is
Mhm.
so massive, right, and so dense that it can just basically collapse on itself,
Right.
and then you see the black hole. So Rudy mentioned earlier, and then we went off on a tangent, and I
Right.
never got to answer this question. He mentioned how, like one example of a creation of a black hole would be after a supernova.
Right.
That's definitely one possibility.
Okay.
You have this star, and the star is just like, dying, and then when it dies, it goes boom, and then when it goes boom, you have a remnant of this star, and if the remnant is small enough but massive enough, it's going to pass some density threshold, and it's
Okay.
going to become a black hole. But this is not necessarily the case. It's not like every star that dies is going to turn into a black hole, because
Right. Right.
maybe, yeah, they are all massive, like incredibly massive, but it's not about the mass, it's about the density. So if you have an object that is like, yay big, and very massive, and you have an object that has the same mass as this one, right,
Right.
but it's this big, this one has a much better chance of becoming a black hole than the other one,
I
because it's
see.
not just about the mass, it's about the density.
That makes sense.
Yeah, so if you look at for example, our sun, if you compare our sun, it's huge, it's really big. If you compare the sun to something like, I don't know, like, let's say, um, uh, if you take our sun and you look at a black hole that has the same mass of our sun,
Right.
we're talking about a stellar mass black hole. That's what they're called, because it's a black hole that has a mass that is comparable to the mass of our sun, right? So if you look at our sun and you look at a black hole that has the mass of our sun, the difference in size is ridiculous. Like our sun is like this big, the black hole is like this.
Okay. Okay.
Wow.
You know,
Okay.
because it has the same mass, but it's just concentrated on this very tiny
Yeah, I
space.
understand
That's
density.
why
Yeah.
it's so dense, and that's where the gravity comes in, because gravity is inversely proportional to the radius of the object.
Oh, so smaller it is, bigger mass.
So
Okay.
the bigger the object is, the weaker the gravity, if that
I
makes
see.
sense.
So if
I get
it's
it. I get
very
it.
small, concentrated, dense, but it has very large mass, then the chances are much greater for a
Yeah,
black
yeah,
hole to
yeah.
occur. I
So
see. That makes sense.
sometimes you have like supernova, like the stars going boom, and you see the supernova, but then the remnant may not be a black hole. It may be, if it wasn't like dense enough, it can end up being something like a brown dwarf, or what's another example?
A funny
Um,
example is Dragon Ball Z. Think about it. When it goes to Kai's planet, it's way smaller, and
That's
that
true.
gravity's way stronger
I
because
remember
of that. You know.
yeah, actually, I would like to say, like, the stage before the black hole, like the next more massive object in the universe outside of a black hole would be a neutron star.
Mm,
Like,
What is
if
that?
some a neutron star is something like that is almost it was very close to become a black hole, but not quite. You
Okay.
still
gotcha.
you still have it doesn't have a horizon, so you can still see the light coming from,
Gotcha.
detect the light. And this actually has opened up a new, now that we can detect the gravitational waveform from this object, it has created a whole completely new subfield in astrophysics, which is called multi-messenger astronomy. Multi-messenger, because now we're getting signal from two kinds of electromagnetic sources. We're getting signal from, if you observe a neutron star, you're looking at light, like regular light that you see on the
Yeah.
telescope, and then you also getting a different kind of wave, which is the gravitational wave. Because before detecting neutron stars, when we first detected black holes in 2015, that was only okay. So before the black holes, you were detecting, light sources, or whether the light was in the visible range, or whether it was infrared or whatever, but it was always light, some kind of light. It was the source was always coming from the electromagnetic spectrum. Now with the black hole, you don't have that, because it's black, you don't see anything, but you're detecting not electromagnetic waves, you're detecting gravitational waves. Because if you look at two black holes, moving around each other, they're generating a lot of waves coming from the merger, right? And all these waves, that's what we detect. So we detect it's a different kind of wave from a spectrum.
Are we detecting that with the same equipment that you were earlier talking about?
Yeah,
Okay.
exactly.
Okay.
So, and now with neutron stars, you're getting both. You get with the black hole, you only get the gravitational waves, because you're not seeing it. But with the neutron stars, you get both. You get the electromagnetic waves along with the gravitational waves. So that's why the field is called multi-messenger astrophysics.
I
When
see.
we're trying to read these waves, is there any dangers to that of like anything around the equipment?
Oh no, absolutely not. There's
Okay.
so many things that I would be worried about before being worried about gravitational waves. Gravitational
I
waves
don't
have
know. You know. Yeah.
No, no, listen, gravitational waves are so weak. That's
Okay.
why it's been so hard to detect them.
Okay.
They
Okay.
are very,
Okay.
very weak.
Well,
This,
no, I
this,
mean the equipment to read it, because it's so weak. You have to build something that strong. That's what I was
no,
saying.
no, it's not about strength, but you have to build is something that is very, and I mean very sensitive.
Okay. Okay. Okay.
It's like detecting a gravitational waves is like the equivalent of finding a hair in a in a in
Yeah, I
a
understand. Okay.
you know
Needle
in
in
a
a
pile of
haystack
in a
sort of
pile of
thing.
sand,
Yeah. 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 Yeah.
in a beach,
I
basically.
gotcha.
Okay.
Yeah, it's
Okay.
really, really hard.
Interesting.
That's why when it was first detected in 2015, the people that worked on that, Kip Thorne and two other dudes, they got the they got the Nobel Prize for physics, because I mean it was a big deal. I only work on the simulations part. I do simulations of black holes, so we have to use high performance computing, which is a fancy word for saying We have to simulate everything on a
Could
cluster.
you explain the hardware in these computers? Because
Thirty
I'm I
ninety 3090
right?
RTX.
Yeah, something like that.
I'm a big hardware guy, and I'm very curious. I
So,
understand because I also do networking, so I deal with servers and all of that. But I'm
mhm.
curious, what would you have to have, horsepower wise, for lack of a better term, to
Just
even be able to
a lot
work
of
with something
memory,
like this?
a lot of memory, because when you're working with all these equations, you're allocating memory for a bunch of objects, so you need a ton of memory.
I
And
mean,
of course,
is a ton 100 gigs? Do you have a
no,
number?
100 gigs is child's play.
Okay, so it's something
Yeah,
far beyond that.
multiply that by a billion.
So, I mean, but we have stuff like this that is
Yeah,
that high?
I have it in
Wow.
my center at the I work at the CCRG, the Center for Computational Relativity and Gravitation at
Okay.
RIT, and we
Interesting.
have like the machines that we have there. They cost millions of dollars, so it's not
Wow.
a joke.
Someone messes
Um,
up, breaks one.
So,
My God, that guy's
you're
fired.
saying it's like in the millions, not even 100,000 gigs. You're
no, no,
talking
100,000.
millions.
100,000, you're gonna buy an RTX 3090 with the prices we have now with the stuff.
Yeah, he's so right.
But
So
yeah, it's cool to try to figure out, some
yeah,
relativity
and
here.
actually, as I move on in my research, I'm gonna be allocated also to Blue Horizons. It's like the supercomputer they have in the University of Texas, and that one is like working on that. It's a pretty big deal because that's like probably the best supercomputer we have in the U.S.
Do you,
It's
do you
really
get
That's
do you
amazing.
get
cool.
nervous at all? Like, is there any way things can go wrong? You can damage it, you can break it. Can that
Nah,
happen?
not really.
Okay.
As long as you don't do like sudo rm and then delete the whole.
Oh my God,
Hey,
imagine.
Can you imagine?
Yo, can you
You
imagine
better
that
be
guy
comfortable
though?
with Linux.
That guy would probably go to jail. I'd probably kill him or something. I don't know. There's no
No,
way.
they would have to kill him on the spot. I mean,
No, no. The good thing about all this stuff is that you can do everything like I can do everything from my laptop because you can do SSH, like remote login to the
okay,
supercomputer, and I can run the simulation from my laptop. And
okay, gotcha.
I'm using a $1 billion computer just from my laptop. I mean that's just
That is
amazing.
pretty cool. Yeah, yeah.
Yeah. So right now I'm not using like that much the supercomputer because at the moment what I'm specifically working on is something called the initial data problem of numerical relativity. And for the initial data problem, you don't really need that many resources. It's a very difficult problem, but it's not a problem that requires that many resources because what
It's human
requires
mind power,
so
not
so so
computing.
basically these are all differential equations, right? And
Okay,
the thing is you have to set up the initial data, like the initial configuration of the system, and then after you set up this initial data, then you evolve the system. And at this time evolution of the system, that's what is really expensive. You do need a
okay,
supercomputer for that. You're not going to be running that on a desktop, no
I got
way, because you need a ton of memory, you need a lot of CPU power. The more cores you can run on, the better. It's not a joke. But for the initial configuration, it's totally doable. Like I do it on my desktop without a
I got you.
problem. So yeah, I'm currently working on that on the initial data.
So, is there anything like what do you right now? What do you specifically work? I mean, you don't have to as easy as you could. What are you actually working on right now? I mean,
Okay, actually working. Okay, that's
yeah,
the hardest part because
yeah,
the more you get into the nitty gritty details, the
yeah.
harder it is
Try
to
to
explain.
keep it broad, I
So
guess. But
so basically, there's this code that is called the Einstein Toolkit. It's a code based called the Einstein Toolkit, and here we have like this. It's basically like a code base. So there's a bunch of codes in this code directory where
okay,
you can solve all kinds of problems in with black holes and neutron stars and whatever. There's one particular code which is called the two punctures in the Einstein Toolkit. You can go to the webpage einsteinstoolkit.org. In this, using this code, the two punctures, you can basically you can define the initial configuration for two black holes. So you set up the initial configuration for two black holes, you give it a mass, you give it a spin, you give it a linear momentum or whatever. And then after you have this initial data set up, Then you put it on a cluster and you run the time evolution of these two black holes, and then you get a merger, they collide, they form another black hole, and you get these gravitational waves and all of this stuff.
Okay.
But my problem right now is that I have this two puncture thing, right, which is basically to set up the initial data for two black holes. But I'm trying to extend it not only to two black holes, I want to extend it to more than two black holes.
Oh, okay.
I want to be able to run simulations for 3, 4, whatever number of black holes we want.
Right.
Now, this is really, really hard. There are some people like from Germany who already they came up with a code a couple of years ago.
You're personally working with different people all around the world on these projects right now.
Not at the moment, because the people that I will be collaborating with at the moment, they are both German and they are both dead. So,
okay.
so yeah, I'm really all by myself on this. Well, I have a lot of help from people from my group.
Sure.
But yeah, I can really go to them and ask them questions.
Okay.
So basically, this other group, German group, they already came up with a code to evolve more than two black holes. But there's a catch. The code they use, it's a lot slower than what I want it to be.
Okay.
Basically, there's this thing in computational mathematics, which is how fast can you make your code converge to a solution? So let me give you an example. If you look at take an interval in the real line from 0 to 1, right? So you go from 0 to 1. In math, not in a computational math, just math in general. From 0 to 1, this segment has an infinite number of points. Right. The cardinality of the segment from 0 to 1 is the same as the cardinality for the entire real line, meaning infinity. You have an infinite number of points between 0 and 1. Now, let's say that you want to do a calculation that involves, maybe implementing a function or something on the interval 0 to 1 on a computer. You don't have an infinite amount of memory, so you're not going to be dealing with an infinite number of anything, right? Okay. So what you have to do is you have to put a number of grid points in your grid. So you start from 0 to 1. Let's say that you want to do 10 points, right? So you have a grid spacing of 0.1 between each point, right? So you go 0, 0.1, 0.2, blah, 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 all the way up to 1, right? So you're working with 10 points. Obviously, when you take derivatives of this function and whatever, you're not going to get a very accurate result because the grid spacing is too coarse. You want something finer. You want to refine your grid as much as possible. Yeah, so instead of using a grid spacing like 0.1, you might want something like, I don't know, 0.001, Right, so you want to have more and more and more grid points. The more grid points you can have, the better.
So you're literally stuck in a trial and error right now, trying to figure out exactly where these points need to be.
It's not trial and error. I'm going to tell you what the problem is now. The problem is that even though you always want this, you want more and more grid points to make your solution more and more accurate.
Right.
The more grid points you use, the more computational resources you need.
Right.
Okay, yeah.
Right. So it becomes really expensive. Imagine that you're doing a computation like you're solving a differential equation and it all boils down to a linear algebra problem, solving a matrix. And you have like 10 grid points and then your matrix is 10 by 10. Okay, that's doable. Right. What if you have 100 grid points? Then your matrix is 100 by 100. And you see where I'm getting at?
Yeah, and you're dealing within the millions and billions and all that.
Yeah, so it can get very expensive. Now, this code that the people from Germany did it's using a method, a numerical method called finite differences. In finite differences, the convergence goes as it depends. It can go as square the number of grid points or the fourth power of the number of grid points. Meaning that, let's say, for example, if you have an h square OH square convergence, for example. If you cut in half the grid spacing, you're getting twice the accuracy on your result, right? Okay. But that's not very effective. What I'm trying to do is I want to extend the two punctures because the two punctures uses a different method, which is called the pseudo-spectral method. In pseudo-spectral methods, what you have is exponential convergence, basically. So like instead of going as h squared or h to the fourth or h to the sixth or whatever, you go like e to the h.
Right.
So it's like everything is just decaying a lot faster. So if you have a problem that you're only using 10 grid points for a problem, and you're using a finite difference method, it's not going to be accurate. If you use the same 10 grid points using a spectrum method, it would most likely give you a very good result. So it's a lot more efficient, basically.
Okay,
So
so
it
we have about
requires, yeah.
5 more minutes here,
Yeah,
and then
sorry
we
guys.
gotta
I
wrap
know
it up.
this is all very interesting. I got a few minutes
Oh,
left.
so you got any questions, Rudy?
I mean, I definitely gave him the few that I was very interested, and I'm happy to hear that. I'll at least give myself a little pat on the back. My black hole definition was not completely off, so I'll give myself a little credit, a little bit. No, I think it was very interesting, man. I feel like we could talk to you about this for like another 3 hours probably, and it'd be I would not be bored the whole time.
I'll be happy to. Yeah, but I also don't want to bore you to death.
No, it's not. Honestly, it's not boring to me at all, and I think Tim feels the same way about
No,
it as I do. Like we just love these topics that we know nothing about, and someone can talk. The way you talk about it, it's cool. It's cool to see someone so passionate about their job and really into what they're doing. So I think that's great, man.
man, you should tell that to my supervisor.
No, you do explain it pretty well.
You do. You make it. It doesn't.
Yeah,
It
I mean,
like,
it's tough because I mean, I like if I just want if I was going to just give you an overview, like this is vaguely what it is and whatever, it's a lot easier. But if we get into the details, it's like you
It's
have
like
to
we
dance
want some
around.
details, but we don't want all details.
Yeah, exactly. Like I'm already talking about finite differences and spectrum methods and all this crazy shit.
Well, Mario, let me tell you, in the time that you've been talking, I have 1, 2, 3. I have like 6 tabs open because I'm gonna go look some stuff up that you talked about. I'm like, I want to know a little more about it. Like,
so usually you see like the galaxies just forming some kind of shape because usually, I mean, this is actually something that no one has been able to prove, and I don't think there's a way to prove it. But like so far, it checks out in every case. All the galaxies that we know of, there is always a supermassive black hole at the center, or some black hole at the center, because you see how the galaxies are.
So if that's true, what about our own?
No, we do have one. That one is a fact. That one is. Okay. I can guarantee you that we have that. So the thing is, like, you see the shape, right, and then you also see it like moving. You see it like spiraling in a certain direction, and it's doing that because it's just circling around the center of gravity of the galaxy.
Do you think it's because of the black hole?
Oh no, it is. It is.
Okay,
I mean,
okay.
There's no other object that can have that kind of a gravitational.
See, I didn't know that our universes was almost kind of working around black holes. You could think of, you could put it that way.
Yeah. One of the reasons why I really want to get into this, extending this code to include more than 2 black holes is because so far all the detections that we received are for binary systems, like 2 black holes that are dancing around each other, and then they plunge and they form another black hole. But one of the reasons why I want to include more than 2 is because we know that at the center of galaxies there are supermassive black holes, and we have, like, around them there's not only stars, not only solar system, there's also other black holes. And the thing is, with the detections that we have so far are, using the instruments that we have here on Earth, like the one from LIGO, the one from Virgo, we don't really get the signals from the supermassive black holes because those send signals at a different range, which is out of our current range right now with these detectors. But with LISA, the one that is launching in the 2030s, we're going to be able to detect supermassive black holes. So this is going to be exciting. So exciting. If I get this rolling and I get this code to work and I get the templates out, when the whole thing comes out, I'm going to be there. I'm going to be like,
one final question.
That's amazing.
Yeah.
Man.
What's going on? Elon Musk, I mean, he's very popular. He's really into all of it. Some people are basically almost against him. Are you for him? Are you against him? Do you think
I'm never against anyone who's pushing technology.
Okay. I just had to ask because I see a lot of hate.
Yeah, maybe he doesn't have the best personality out there.
Right.
Maybe, I mean, he's not perfect. None of us are.
Yeah.
I don't care. The only thing that I care about, and again, one thing, no one deserves to have all that money. Like, it doesn't matter what you do. No one deserves to have all that money.
I definitely agree.
There's too much poverty in this world. But anyway, that's another topic that I don't want to get into. But anyone who's pushing technology, man, I always appreciate them because we need that. We need those people. We need people that are taking chances and taking strides and pushing the technology forward. You know,
Very cool.
and that's
Okay.
why I love Apple, for example. Like people, you can say whatever you want, they're overpriced and whatever, and it's all true. Like
It's all
the
true, but I like
criticisms,
them too.
but
I'm
I
with
like
you.
them because they push the industry.
Yeah.
Yeah.
Who was using USB-C before them? Like when we saw that for the first time, I'm like, no, I don't want to use dongles. Like, why would you come up with this USB?
I think
Now everyone wants USB-C because no one can put the USB-A on the
the
first
right
go.
way. The number one most important thing about what you just said is that the competition needs to exist always. Because man, that always pushes everything forward,
Now
always.
look at Intel was taking it in the gut now
right.
with AMD and with the Apple Silicon. They were like drowning now, and they just came up with this fantastic chip that just came out recently. Have you seen the reviews for? I think it's Alder Lake is what it's called.
I saw
The
something
latest
about
chips.
it. I didn't look into it much.
It's blowing everything out of the water.
Awesome,
Nice.
man.
I mean, we could take back to the beginning of our episode in general on video games. Of course, if there was no competition, we'd still be with Atari sticks.
Mm-hmm.
You know what I mean?
And that's why I don't understand fanboys. I really don't.
It's so silly.
Like, I'm over here like, hey, let them rip each other apart. That's what I like.
Right.
I want.
Yes.
Yeah.
No, man.
They need to like up each other, and that's how progress gets made. Yeah.
Well, listen, Mario,
Anyway,
thanks for coming on, man. That was awesome. Very interesting.
Thank you so much, guys, for having me. And anytime, man. Anytime, whenever.
You're welcome. Anytime, man. Whenever we're looking for more people to come on and stuff, we'll reach out to you for sure. So.
Yeah, thank you so much for coming on.
Yeah, thanks for taking the time.
All right, I'll see you.
All right, fellas.